I think we're all set to begin. So yeah, once again, I was just really saying that this is something I thought about, and it's really amazing to see Dr. Barlow get this movement going. You know, where folks are able to teach courses online for students for free to provide some, education around varying topics that are of use to the general public. And I don't think organic chemistry is something that should be as inaccessible as it is. I think it's a very exciting subject. I think once people start learning it and realizing how it's connected to their daily lives, they'll find it fascinating. And hopefully through these series of lectures, I'm going to be able to encourage many of you to think about taking organic chemistry as a course and not be terribly scared about it. So I will be giving a number of lectures in the coming weeks. I'll be, teaching about things like acid-base reactivity. Drawing Lewis structures is probably my number one goal. I would really love for all of you all to leave these lectures being able to draw Lewis structures comfortably, to be able to recognize functional groups so that when you read the back of your labels, you're like, I know what an acid is, I know what an alcohol is, I know what a ketone is, etc., etc. And then also maybe to identify functional groups using techniques such as spectroscopy and spectrometry. And we'll see how far we get. I'd love to show you all some reactions. We will do some mechanisms. We'll learn how to push arrows. We'll do that with acid-base reactivity. And we'll see how far we get. So let's jump in. So before we start, why don't we go all the way back to the 1800s? Okay, it's a little bit of history. And back in the 1800s, you had folks like John Dalton. I said late 1700s, early 1800s. Folks like John Dalton, Antoine Lavoisier, and Berzelius were people who really made chemistry or brought chemistry to the forefront. And I'm singling out Berzelius here because he really made some significant contributions, including, he discovered a number of the elements. But he also developed a system for chemical notation. So we write H2O, it's not written properly here, but we write H2O the way we write it, with 2 as the subscript. He actually started off with 2 as a superscript, which indicates the number of hydrogens that are in this molecule, right? So H2O means there are 2 hydrogens in the molecule, there's 1 oxygen in the molecule. He also came up with the 1 or 2 letter representation for elements based on their Latin names. And so because of all of that, he was considered the father of modern chemistry. And he coined these terms: organic from living things, inorganic from non-living things. And also this theory of vitalism or vital force theory, he really pushed that, although it was really developed by others before him, where this theory was one that, simply put, you had to have a vital force. You had to be a living organism to make organic compounds. So organic matter couldn't be synthesized in a lab. It had to come from a living source, so animals and plants. And so because of that, no one really, I would say at the time, were thinking about making organic molecules. Inorganic compounds are very common, salts and so forth. And so that theory of vitalism was born until Friedrich Wöhler in 1828 disproved this vital force theory, right? What he did was he was able to show that you could take this inorganic salt, ammonium cyanate, and if you heated it, it would convert into urea. And you've all heard about urea before, right? Urea is a byproduct of protein metabolism in the body. And that happens in the liver and it's cleared through the kidneys and we pee it out, right? So this is the structure of urea. So urea has, you can see in the box I've drawn it out, it has a nitrogen atom. And for nitrogen, that is connected, is bonded to 2 hydrogens. It's also bonded to a carbon. And that carbon is double bonded to an oxygen, which is then single bonded to another nitrogen and 2 hydrogens, right? Now, that is one representation of this. We call this a Lewis structure. And we're going to talk about what Lewis structures are, and I'm going to teach you how to draw them. But there's another representation. We call this the line angle representation. And this representation is one where carbon atoms are written as points. So you might see that this point, the difference between these two molecules is this point right here, right, is actually a carbon atom, right? We don't write C's in the line angle formula. We just write a point, and that simplifies it. And the reason why we like to do that is because there are so many carbon atoms in organic molecules. Organic molecules, carbon is the backbone of organic molecules, the backbone of life. And so you can imagine once you start drawing larger molecules that have 20, 30, 40, 50 carbons, you'll be writing C's like crazy. And so we needed a short way to write it, and we just write it as a point. Every other element, we write them out. So you can see in the second version of the formula, the nitrogens are still present, the oxygen is still present, only the carbon is removed and denoted as a point, okay? So basically what happened now is Friedrich Wöhler literally disproved this vital force theory, which means people can make organic compounds. So we don't have to use living organisms or depend on living organisms to make it. We could potentially now make organic compounds in the lab. And so he's deemed or considered the father of organic chemistry as a result. Because really, if you think about it, this is the very, very first example of an organic reaction or the synthesis of an organic compound. And because of that, everyone else got interested, right, in making organic molecules. And a notable one in 1845, I want to point out to you, was Hermann Koebele's synthesis of acetic acid. And this is the first multi-step synthesis, meaning this was the first synthesis that you could showcase a multiple steps. So you're starting here from elemental carbon, just carbon, the atom, right? Elemental carbon. And in 5 conversions, he could make that into acetic acid. So when we say multi-step, we're thinking you take carbon, do a reaction. We're not going to go into details of the reactions he did. He did one reaction and converted the carbon into something else. Then that something else, he did another reaction on that and converted that into a third molecule. And that's the number of conversions we're seeing. So 5 conversions led him to acetic acid. And what I'm showing you here are 3 different representations of acetic acid. You've already seen 2 types of representations. I'm introducing a third one to you. The first one is going to be our immediate focus in the coming lectures, and that is once again the Lewis structure. So this is the Lewis representation. Why is this looking like that? 1 second, let me get my pen. All set. Yes, I want a pen. This is the Lewis representation of the molecule. This is the condensed representation. And this one is what we call the line angle representation. Okay, so these are 3 ways to write the same molecule. And so the first one on the left, you can see we're clearly writing out all the atoms and every single connection it makes. So you see there's a carbon and it's making 4 connections, 3 connections to hydrogens, and then it's making a 4th connection to another carbon. Let me zoom in so you all can really see this online. So you can see that it's making 4 connections, 3 to hydrogens, 1 to carbon. That carbon is now making 2 connections to an oxygen and a single connection to another oxygen. And then that oxygen is making a single connection to a hydrogen. I promise you, you're going to be able to draw this easily. I promise. Okay. But then the other representation, this is what we call the condensed formula. The condensed formula is a shorter way to write it. We're just writing the elements. We're not showing the bonds. And what you're doing is you're looking at the main elements that are pretty much written in a row. You're kind of looking at these elements that are written in a row, the main ones. And then what you're doing is you're writing what is attached to them. So the carbon is attached to 3 hydrogens, CH3, and then it's attached to another carbon that's attached to 2 oxygens, which is attached to a hydrogen. So this is a short form of writing it. We will not really write it like this very much. You might see it in the text, but that's a way for you to appreciate when you see this version. Now, once again, the first version is one way we'll practice a lot, but eventually the third version is what we will get at. And then to reiterate my point from earlier, you can see here that these are 2 points, right? Every time you see a point, that is a carbon atom. And that's how we do it. So there's a carbon atom at the front, there's another carbon atom, and then every non-carbon connection is written out as the atom that it is. So the carbons are really just implied by points. Every time you have a point, and then the line just keeps bending. What's also implied is the number of hydrogens that are attached to a carbon. And that I will also teach you later, and we'll save that for a little bit. Okay, so once again, Hermann Koblé was able to synthesize acetic acid. Question for you all. All right, your first question of the lecture. Does anybody know where they can find acetic acid in their household, in their kitchen? Where do you find acetic acid?
Vinegar.
Vinegar, exactly. Thank you so much. So vinegar is a 3 to 5% solution of acetic acid, and we use vinegar a lot, right? So now you know the structure of vinegar. This is the structure of vinegar, and you can draw it 3 different ways. All right. Let's go. All right, so next slide. So we're moving through the years, right? So we're at 1845, and you can see that organic chemistry is becoming very much sophisticated at this point. We just talked about a synthesis of acetic acid, right? And now we're talking about a synthesis of, what is this? A synthesis of where's my eraser? Oh, there we go. I'm not sure what it's doing now. Okay. And now we're talking about a synthesis of indigo. So if you look at indigo, indigo is a large molecule, right? It's such a large molecule. And this is a good example of why we don't write all of our carbons out. Imagine writing all these carbons. Remember, carbons are represented as points, as I mentioned to you. So let's identify all the carbons. This is a carbon. This is a carbon. That's a carbon. That's a carbon. That's a carbon. Carbon, carbon, carbon. Every time it bends, if it's not a carbon, we write what it is. If it's a carbon, we write it as a point. Those are all the carbons in the molecule. So this is why the shorthand notation is really excellent, because you can just draw a large molecule really quickly if you don't write out the carbons. And carbons are going to be overly represented in our molecules. Another question, does anybody know where indigo can be found? I'll give you a hint. Many of you are wearing it as we speak. Yes, denim, jeans, exactly. There are approximately 5 to 8 grams, I think, don't quote me on that if I remember correctly, of indigo per pair of jeans. So that's what gives the indigo, the jeans, the color we see. It's a beautiful dye. Okay, so moving on to the 1900s, we had people like Robert Robinson and others who started, you know, that they've learned how to manipulate molecules into larger organic structures, started to make things that have biological implications, like drugs. Particularly in 1930 to 1964, people became fascinated with steroids, right? And so steroids, cholesterol, I'm showing you here the structure of cholesterol. Every steroid, by the way, has the similar structure, and every steroid has these rings, that ring, that ring. Every steroid has a 6, 6, 6, 5 ring system. You can see that ring system in cholesterol. You can see that exact ring system in cortisone. And that's what every steroid will have. Anytime you see those atoms in that specific order, that is a steroid framework. All the other attachments beyond those 4 rings in that order make the steroid a particular molecule. So cholesterol versus cortisone will have different connections. And so you can see the molecules keep getting larger and larger as chemists learn better and better to manipulate organic molecules into more useful structures, right? Around this time, penicillin was isolated and all those other compounds. Okay, so moving on to a little bit later, we can move to the 1940s to 1972, when people started getting really, really interested in synthesizing molecules that already exist in nature. Basically, if you think about a lot of molecules, they don't exist in large quantities. So the question is, can we synthesize them in a lab and synthesize them in enough quantities that people can use them, right, for addressing disease, etc., etc. And so this synthesis here, a lot of folks went about synthesizing things like chlorophyll A, synthesizing penicillin, synthesizing quinine. All right. So anybody knows where you can find quinine? One question. Where can we find quinine? Some of you might drink it. That's a hint. Yes, tonic water. That's correct. So tonic water has a lot of quinine in it. Anybody knows what quinine cures? What does malaria exactly? So quinine is very good at curing malaria. So organic molecules are everywhere, and I just want to impress on you that you use it every day. Your body is made up of organic molecules. You eat organic molecules. You use organic molecules to address your health issues, right? And so I think it's very useful for you to do it. And are some pharmaceutical compounds that are organic compounds that you might be familiar with. You all know Viagra, which started off as a heart drug, but the side effect was more financially viable than the actual heart condition. And so Viagra became used for a purpose we're all aware of. And then Valium is an organic molecule. Aspirin that we take, many of us, there is the structure of aspirin. You can appreciate its structure now that we talk about carbon atoms. It's not a very complex molecule. It was first observed when people were chewing on the barks of the willow tree, and that would cure their disease, their headaches. And chemists were able to isolate this molecule and show that it is actually that molecule in the bark of the willow tree that is having that effect. And then, of course, Lipitor, which is a fantastic molecule that was synthesized out of Pfizer, I believe, for cholesterol. Okay. But of course, I've been on TikTok for a while, and I've since being on TikTok become really into skincare because of all the videos I see all the time on my social media platforms, to the point where I've actually found my own skincare routine. And so I'm sharing you my skincare routine with you that I've developed from the thousands of videos that I've seen. So I start off my skincare routine with a nice little cleanser here. That's my cleanser of choice. All right. Oops. And then after that, I, wipe my face with some ordinary glycolic acid. And this is the structure of the glycolic acid that is in your ordinary kit that you take, right? So this is a structure of the glycolic acid. And then that's an organic molecule, right? Now you know how many carbons. There are 2 carbons in this organic molecule. Here it is. We can highlight them there. They're represented as points. And we have 3 oxygens, right? And then are we twins? I saw a comment. Yes, we're twins. Look at that. That's crazy. And then I use the Anua niacinamide and tranexamic acid compound blend, I should say. And this is the structure of niacinamide, right? You can see that it has a bunch of carbons in there. There are all the carbons, nitrogens, and oxygens. I hope you're seeing a trend here that literally the vast majority, if not all organic molecules, is really a combination of the same 4 or 5 elements. It's like carbon, nitrogen, oxygen. Those are the main 3. I like to call them the holy trinity of organic molecules: carbon, oxygen, and nitrogen. Literally, those are the 3 molecule atoms in like 1,000 different arrangements that can make almost anything. And then, of course, tranexamic acid. I've removed the 3D portions of it. We'll save that for later. You can see the carbons in there if you want to highlight them. One here, right? I think you guys are getting good at this. These are all the carbon atoms present in tranexamic acid. And then caffeine is what I use. I use that under my eyes, right? So I put a little bit under both eyes, and then I leave it there. And this is the structure of caffeine that you take, like you drink every day. That's what's in your coffee. And that's what people put on their eyes. And then finally, I use this facial moisturizing lotion that has SPF 30. And it has this UV protecting agent that is homosalate. So that's the UV protector. And there's a structure of it right there. You can see it has a lot of carbons and oxygens. But one thing I want to point out to you all is a word that we've been using a lot: acid, 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 right? And for organic chemists, acid really means a specific arrangement of atoms, okay? And we're going to talk about functional groups at some point: alcohols, acids, ketones, amines. And really, what functional groups are, they are a specific arrangement of atoms that allows that part of a molecule to have a particular function, right? And so you notice in both names, tranexamic acid, glycolic acid. Take 10, 15, 20 seconds and see if you can find what unifies those two molecules. So what portion of glycolic acid is identical to that portion of tranexamic acid? Take 30 seconds. I see some comments in the on the live and on the Zoom. I think y'all are such good students. My God, you don't need this class. Let's just log off. I'll give you the test right now. So yes, that's correct. Tranexamic acid and where's my erasing function? Okay, there we go. Thank you. So tranexamic acid and glycolic acid, they have this unit in common. There we go. Why is this not pencil? Yes, they have this unit in common, right? And if I were to write it out, it's a carbon atom, right? A carbon atom, that's what this point is, double bonded to an oxygen, single bonded to an oxygen, that is single bonded to a hydrogen. That unit is a carboxy group. It is what makes things acidic. It is present in acetic acid, if you remember the structure on the previous screen. It is present in citric acid. It's present in tartaric acid. Any acid that we use as an organic molecule typically has that recurring unit. If you want to join the Zoom version, if you go on the website in the link, the website in the link on the link in my bio, there's a link to the Zoom, and I can let you into that as well. It looks the same, but you'll be into the Zoom. Okay. All right. So that is my introduction. Everything comes back to all of these elements, right? And we're going to talk about them a lot. But the whole point is organic molecules really feature one part of the periodic table. If you look at it, carbon, nitrogen, oxygen is right there at the top right. That atom and the one in and the hydrogen, those atoms are literally the main atoms that we keep adding together and building up to build everything, to build up your sugars that you eat, to build up your proteins that you take, to build your entire body for the most part. It's really all of those atoms. And we're going to spend a lot of time talking about these elements and really learning how to appreciate them. So before we can talk about molecules, we have to talk about atoms, and we have to talk about bonds, and then we can talk about molecules and compounds. As I mentioned to you all, today's lecture really is kind of a introduction. And so we're going to jump into a beautiful discussion of some of the, where is it? Let me load this other file. Okay, of atoms and molecules. So let's get some definitions and some words. We're not going to use a lot of these. We are going to use them all, actually. What am I talking about? But just so you have some kind of a understanding of the terminology we use a lot, okay? And then I'm going to give you a little bit of a test. So what is matter, right? We use that word a lot. Matter is anything that occupies space and has mass. In other words, the stuff that makes up the universe, right? So that's what matter is, everything, the stuff that makes up the universe. But we can get even smaller. We can go further, to smaller, the microscopic level, and talk about things that are smaller. So the element, what is an element? So element is a simple substance that cannot be broken down into smaller parts or changed into another substance. And that's what our periodic table shows you. It shows you all of the simplest substances that exist. And those represent the building blocks that we use to make compounds and molecules, right? So an example, like on the periodic table, sodium. Sodium is an element. Now, an atom is related to an element because it really is just the smallest unit of matter that retains all the chemical properties of an element. So if you can think of an element, you can throw out something like, this is not an element, but this is a good analogy. If you think of sand as an element, an atom would be a grain of sand, right? It's the smallest unit of the entity or the substance that still has the same properties as the substance, right? So we're looking at the atomic level, like one unit, simplest unit when we use the word atom, but we often use them to talk about each other, right? An atom is the smallest version of an element, so it's the same thing. A molecule now, we use that word when we talk about a group of two or more atoms, and these two or more atoms, they form the smallest identifiable unit of a compound substance, a substance that's not just the pure element. So oxygen is a molecule, and that's because you have two oxygens connected together. So there is a molecule. It's no longer just oxygen by itself. Now, this is where it gets a little bit tricky because people use the word compound and molecule synonymously, but they're different. And I'll explain the difference to you. A compound has to be two different types of elements, right? So water is a compound because that has a hydrogen and it has an oxygen that together give you that compound. So for example, O2 is not a compound, it's a molecule specifically, but water is a compound. Does that make sense? Because it's multiple stuff, multiple atoms or elements, but they're different, right? So that's a very nuanced explanation of those two. People use them synonymously, but they really are different. So you can think of it this way. A compound is a molecule, but a molecule isn't necessarily a compound, right? Okay, so get accustomed to those words. You have a test right now. I'm giving you 30 seconds to know what those mean. Element, atom, molecule, compound. Make sure you understand all those four right now. Take a screenshot of the definition or the example because your homework is coming in 5, 4, 3, 2, 1. All right, test yourself. So describe the following as elements, molecules, or compounds. Let's see. So we have bromine, we have NaCl, we have Cl2, CO2. Let's go all the way through this list. And this is your first quiz. If you get all right, if you get how many? I have 9 of these. 9 out of 9, you give yourself your first grade, all right? So let's walk through this. I'll give you all 30 seconds each. So let's start off with bromine, Br. So Br, compound, element, or molecule. Which one is it? All right, I see my folks online slaying. Very easy. We started you off easy. Next one, NaCl. Let's figure that one out. Is that a compound, an element, a compound, or a molecule? All right, this is a compound. This is too easy. All right, Cl2, element, compound, or molecule? By the way, NaCl is sodium chloride. Yes, I see it in the comments, table salt. I love that. So Cl2 would be best described as a molecule because it's not a compound, right? It doesn't have two different elements. Very nice, I see that. What about CO2? This is carbon dioxide. Eventually we'll get to naming and we can talk about how we name these things. So this is a compound, right? Because we have two different elements that are coming together to make a unit. CO2 is a unit altogether. All right, next one, P. That is phosphorus, and you'll get to know these pretty soon. Phosphorus is indeed an element. Excellent job. Excellent job. All right. Ca. Ca is calcium. That is also an element. Very nice. And then we have C6H12O6. Y'all are like firing these off as if like it's nothing. I gotta ramp up the difficulty level of this class. So yes, this is a compound. And yes, I see someone say glucose. Yes, this is a structure of glucose. There are other sugars that have this formula, but one compound, sorry, that has this formula is glucose indeed. What about S8? S8 is a molecule. This is sulfur. Sulfur typically exists as S8 in other forms. Very nice. And finally, we have we have H2SO4. That is clearly a compound. Anybody knows what the name of H2SO4 is? What is that? That is sulfuric acid. Very nice. That is the formula for sulfuric acid. All right, you guys are so good. We're moving on. We're getting closer to the organic chemistry part of it. This is just still the review. I hope we get there in a few minutes and we can start talking about bonding. So, of course, we've talked about our atoms. We need to go to the fundamental level and talk about what's present in these atoms and where things are located. So this is an example of the atom. You can see that circle there in the bottom. And the center of the atom is the nucleus. And this is where the protons and the neutrons can be found, right? They can be found in the nucleus of the atom. And then the electrons are somewhere outside of that. Now, there are a number of ways to describe the atom, and there are some primitive ways that people started off with. And the people moved on. The Bohr model this is the Bohr model representation. And there are more fancier ones like the Schrodinger. We're not going to use a fancy one. I really think that the Bohr model for our purposes is sufficient. And so what this really shows you is that the protons, which are positively charged, are housed in the nucleus. So are the neutrons. They have no charge. And the electrons, which have a negative one charge, and they weigh basically nothing, they are found around the kind of orbiting the nucleus. Okay, and we'll leave it there as kind of a simplistic version of it. So where they are is important. We're going to talk about that, but quickly, this is a side track. We don't really need to know all of this information for what we're going to do, but since we're going through the foundational stuff, we should talk about it really quickly. This is kind of how you'll see atoms represented, right? You'll see the element in the middle there. You'll see them write that E for element. It could be hydrogen, helium, lithium, right? And then there are two numbers that you'll see. The number on the bottom left tells you the number of protons. And we're going to talk about the periodic table shortly. The number of protons are shown on the bottom left. And then the top left is the number of protons plus the number of neutrons. So if you want to know how many neutrons there are in the nucleus, you would just subtract the number of protons at the bottom from that number at the top. So really, when I think about the numbers you see next to the elements, they're really telling you about what's in the nucleus, right? So the protons and the protons plus the neutrons. Now, how do we figure out the electrons? That's the question, right? The number of electrons in a neutral atom normally equals the number of protons, right? So the number of protons and number of electrons are the same in a neutral atom. They're not the same in a positively charged or negatively charged atom, but there is a way we can figure what the number is. And that's exactly because it's positive or negative. That tells you how many electrons you've gained or lost with respect to how many you would have had if it was neutral, which is identical to the number of protons. Does that make sense to everybody? You following that? Okay. So here is an example of an atom, carbon, that has all the
I'm sorry, could you repeat it again? I'm sorry.
Yeah, no. Let me repeat that again. Yeah. So what I was saying is, when you look at let's go back to that slide. When you're given, for example, this carbon, let's do an example. If I have hydrogen, okay, and it has 1 and 1, that's telling me that I have one proton, right? We agree. This number tells me how many protons I have. And then the number at the top tells me how many protons plus neutrons I have, right? So because the number is still one, I have 0 neutrons. Does that make sense? Because the top number is the sum of protons plus neutrons. The bottom number is always the protons, right? Now, I'll tell you that there are hydrogen atoms that if it
Yes,
has
that makes
one
sense.
neutron in it, then it could have a number here of 2, and then that would indicate that you have 1 neutron. Does that make sense? But if you don't see that number being
Yes.
2, then it would have 0. Got it? Great. Now, what I'm saying to you, and let's look at another case, is if I see
Yes,
the
I'm on a delay.
normal
Thank you.
hydrogen, actually, do you mind? I'll mute you, sorry. So if you see a normal hydrogen, how we will know how many electrons there are is you would have a charge at the top, right? Remember, the number of electrons is equal to the number of protons if it is neutral. If it is neutral, the number of protons must be equal to the number of electrons. So in the top, in this case, the number of electrons is equal to 1, right? You have 1 electron because you have 1 proton, right? Now, in this version, you have a positive charge. A positive charge means you've lost a negative charge, and electrons are negative. So you've lost 1 electron. So basically, this is telling you that you have 0 electrons. So what you're going to do is you're going to use the charge to tell you how many electrons you have with respect to how many you should have had, right? So if there's no charge, your protons is equal to your electrons is equal to the number of protons. But if there's a charge, you would adjust that number, and that will tell you how many electrons you have. Let's do another example then before we move on. So if I gave you chlorine, for example, and I have chlorine 1735 and minus up here, right? So let's think about that. How many protons would this chlorine have? Anybody? 17, right? Because this number is always the number of protons. How many neutrons does this proton have? This proton has 35 minus 17, which means it has 18 neutrons. Now, how many electrons does this chlorine have? Well, it should have 17, right? It should have 17. But there's a negative charge, which means it gained 1, which means it has 18 electrons. And that's how you do it. Does that make sense? Great. All right, now we know how to calculate protons and electrons. We're experts. Let's move on to where we were saying, what we were saying. So here's a carbon atom. We have one last thing to talk about before we can truly get into stuff. Here's the carbon atom, and in the carbon atom, which looks like this, carbon has 6 protons. It has 6 electrons and 6 neutrons, which means it's 12. So that's what carbon looks like, all right? And we're looking at a neutral carbon, so I'm not putting a charge. That means the electrons are also 6. Great. So what we're trying to do here now is finding out where are the electrons, because that's going to be very important when we draw molecules. We need to know where they are. So what I'm showing you here is really a location that we're going to use. Only two electrons can fill in the first energy level or orbital nearest the nucleus. So the nucleus has the protons and the neutrons, and you can see around it, this very first layer, if you want to think about it that way, where electrons can live. That very first orbit can only accommodate 2 electrons, right? And we like to call those electron shells. It can only accommodate 2. I like to tell people, you got to fill it. You think about it, as you have 20 electrons, and you're trying to fill them into into these homes, right? Think of it as an upside down apartment building, like if it's a pyramid, right? The nucleus is the earth, and the apartment is on top of the nucleus. But the first floor only has two apartments. It can only hold two apartments, right? And that's as much as you can have. And then the next floor, the second floor, that can hold 8 apartments, right? The third floor can hold 8 and sometimes 18. And as you can see over here, this is how we think about it. And that's how we know where our electrons are. And we're going to keep it at this very simplistic level, right? We have 2 in the first level of the apartment complex. This apartment complex might blow over very easily. If you live in like a windy city or somewhere. So 2 houses, 2 apartments on the first floor, 8 apartments on the second, 8 apartments or 18 on the third floor. And you have to fill them from the bottom up first. So if I know how many electrons I have in my atom, I can tell you exactly which level all of the electrons are. This is extremely, extremely important because the electrons we care about when we think about bonding are the electrons that are in a level that is not full. Basically, once a level is full, that level becomes unreactive, it is stable, it wants nothing to do with you. You're going to have a hard time manipulating those electrons in that level. So if you have an apartment building or an atom where you have 2 electrons on the first floor and the second floor has 6 electrons, that floor you can manipulate, and those electrons are what we call valence electrons, right? So that's what we care about. We care about the valence electrons, and these are in the level that is unfilled. Whichever level that is the level that we care about. We want to know about the level that is unfilled, because that's the level that's going to tell us about the bonding properties of that atom, which is what we need to know in order to draw those really pretty pictures I showed you, carbons and oxygens and hydrogens attaching to each other. Right, I love that. Valence equals vacancy. That's correct. I love that. Thank you. And so this is what we need to figure out. All right, let's keep it moving. So we're done now with the intro stuff. We kind of are done with the very, very, very intro stuff. And so what we're going to do now is we're going to move forward now that we've talked about bonding, and we're going to try to talk about, now that we've talked about atoms, now let's talk about bonding. And if you go on the website, I have this document already posted, so you can like take this document and you can annotate it. I'm going to annotate it right now, and let's talk about bonding. Okay, so when we think about bonding, there are 2 main types of bonds that we need to familiarize ourselves with. And those are ionic and covalent bonds, okay? And we really have to look at the periodic table, which will pull up shortly, to really emphasize this point of why the valence electrons, or the electrons in the highest level, are really what we need to figure out how to do this bonding. So in an ionic bond, I'm going to talk about this for a second, and we're going to go back. In an ionic bond, this really involves transfer of electrons. So the electrons are going from one atom to the next, right? So you have like a sodium atom and a chlorine atom, and one of them is giving the other electrons. And the reason why this is happening is because the elements really want to have a filled level. It doesn't want 6 apartments out of the 8 filled. It wants all 8 to be filled. All right. And so atoms are trying to gain electrons, right, to fill that level. Or alternately, it might want to give up electrons so that it can have a filled lower level. So the level, it wants it to be either empty or full, right? And so it'll do what's easiest to get there. Okay. And so you can imagine the apartment buildings or the atoms that have 1 electron in a level would probably want to give away that electron because they have 1 lower that's filled. And the ones that have 7 or 6 in a level, might more than likely are trying to gain the added electrons to fill that one up, and they get filled, right? And so in an ionic bond, what's happening is one atom is saying, hey, I'm going to give you an electron and I'm going to become full. And the other atom is saying, I'm going to take this electron and I'm going to get filled. And so the classic example is sodium chloride, okay? So if you think about sodium chloride, you have NaCl, okay? But let's look at them in their neutral state. Na, if you look at the periodic table, Na has one electron, only one electron. And let me pause and show you how you can figure out how many electrons each atom has. I'm going to pull up a periodic table here for you all so you can see this, okay, down the bottom. Everybody can see that periodic table. Let me expand it. So you can see on the periodic table that all the elements are represented. If the element is over here, then this is one electron, right? Because the periodic table is organized that way. It's organized by levels. This is level 1. This is level 2. This is level 3. This is level 4. Do you see that? And you go across. Those are the levels, okay? And so level 1 is hydrogen and helium. And it should make sense to you because level 1 can only hold 2 electrons, which will say that the atom has 2 protons. So you can only have 2 elements that have electrons that are in the first level, right? So hydrogen and then helium. But if we go to the next level, hydrogen has 1. These elements, all of these elements have 2 electrons. Let's skip the purple box. That is the transition metals. That's for later. These have 3. These have 4, these have 5, these have 6, these have 7, these have 8. And that is why the ones on the right side are what we call the noble gases, right? The noble gases are the ones that have 8. They're like, hey, I'm literally full. I don't need to interact with anyone. I don't need your electrons. I'm not going to give you any electrons. And so I'm chill, right? So column 8 are the noble gases, right? They are very, very, very happy. And so you can figure out immediately by looking at this and numbering the way I did, how many electrons those atoms have in their valence. So if you go across, hydrogen has 1, helium has 2. Helium is full because the first level is only 2. Then we start with the second level. Lithium has a full level, level 1. And in the second level, lithium has 1. Beryllium has 2 in the second level. Boron has 3. And keep going and keep going and keep going until the second level is full again. We have neon. And then we start the third level, the same process over again. Now, this is where you can have 18. When you get to level 4, you can start counting those purple boxes, and there are 10 of them. That's why it can be 8 or 18. Does that make sense? That's how we can get to 8 or 18 level 4 and beyond. Okay, so with that said, we can literally know how many electrons it should have in its unfilled level, or the valence electrons as I just described. So let's look at that. So sodium has 1. Chlorine, it has how many then? How many electrons does chlorine have in its in level 3? How many electrons we can see? It has 7, exactly. And you don't have to write these numbers down. You just need a periodic table. The periodic table is the chemist's Bible. If you have a periodic table, so much information you need, you just look at it and you can tell, right? So chlorine has 7. You can draw them like this. They're really paired, or this one is unpaired. We can talk about that later. And then we have the most perfect situation set up, right? Sodium is like, I want a filled level. I am in level 3 and I have 1 electron in level 3. It doesn't make sense for me to beg atoms to give me 7. I should just give somebody 1, and then I'll have my lower level full and I'll have all filled levels. Chlorine is like, hey, I have 7, I just want 1 more. Who wants to give me 1 more? So sodium is like, hey, chlorine, I know you want 1 and I want to give away 1. We are a perfect match. So sodium gives 1 to chlorine, and everybody's happy. What that means now is sodium is positively charged. We just talked about that. If you have 1 less electron than you have before, you're going to become positively charged. And then chlorine gets one more. If you get one more electron than you have, you're going to become negatively charged, right? And so these atoms are now ions. Once you have a charge, you are now an ion. And these ions now attract each other. So an ionic bond, right, by definition, is really the electrostatic attraction between two ions. That's why it's called an ionic bond. One that's positive and one that's negative, opposites attract. So because sodium has a positive one charge and chlorine has a negative one charge, then they attract each other and we write it as NaCl because then there is no overall charge. Plus cancels minus, they are happy. But your job now and going forward will be to be able to recognize when an ionic bond exists, right? And so a common way of thinking about it is these columns, these two columns on the left, these are going to very, very happily give up electrons and become positive. This column is always happy to become positive 1. The second column is always happy to become positive 2. And then these over here are going to be very happy to become negatively charged, right? This column, column 7, is going to happily become negative 1. And column 6 is going to happily become negative 2. And because of that, those elements will always like to form ionic bonds. So if I see something that is KBr, I know that's an ionic bond. I know that's a potassium that is +1. And that's a bromine because it's in column 7, that'll be a -1. And those two will come together and make a ionic bond. So the ionic bond has to be an attraction between a positively charged an ion and a negatively charged ion. Does that make sense? And this is a giveaway for ionic bonds. No, we don't typically see a lot of ionic bonds in organic molecules. So while I'm explaining this to you now, it's important. We will see it and you need to appreciate it. But this is very common in inorganic bond molecules. And that's because there's a significant electronegativity difference between these atoms, which cause them to have these properties of being more positive or more negative. And then they will want to form positive or negative charges and attract. It is a totally different situation, okay, when we go and look at covalent bonds, okay? So let's do that. Let me get rid of, oops, I might need to move this. I'm trying to navigate these files and my, let's just reopen this. Yeah, so we just talked about NaCl, right? Being a ionic bond, which is equal to Na plus and Cl minus. That's what they are. So a covalent bond now involves sharing of electrons. So instead of giving an electron away, they're sharing them, okay? So, and that's gonna happen when the atoms are like, listen, I want more and you want more. I'm not gonna give up this many electrons. You're not gonna give up this many electrons. Why don't we do a sharing agreement? Okay, like let's share and make a pool that we can pull from. But I'm not trying to give up all of my electrons to you. You're not trying to give up all of your electrons to me. Let's just share them. Okay. And those are the types of bonds, covalent bonds, that you will identify or see that are prevalent in organic molecules. So let's do an example and show you how you can figure out how many bonds an atom is going to make in a covalently bonded scenario. So let's look at carbon. You have your periodic table. I'm sorry, I need to pull it up again. Let's see if we can, if I can pull it up again. Files, here's my periodic table. That's on the ready. Pulled down, perfect. So carbon, let's number them again. This is gonna have 1 valence electron, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Pardon my chicken scratch. So carbon therefore has 4 electrons in its valence. So carbon wants 4 more, right? So if carbon wants 4 more, this is why carbon's in this scenario. It's like, I want 4 more. And the other atoms, it's not going to give up 4. That's a lot to give up, and it's not going to. No one is going to give it 4, right? So that's a lot to give up as well, right? So how can you do it? You can share. So let's think about carbon, and let's think about it reacting with, for example, hydrogens. So carbon needs 4 electrons. So this is very important for you to understand. If you are going to be in a true relationship with someone, all right, now listen to all these people who are in these relationships with these like awful people. A good relationship is one that involves equal sharing. Okay, so don't sell yourself short. Okay, make sure that if you're bringing 1 electron to the table, he's bringing 1 electron to the table. All right, that's a good bond. That's a good relationship. So carbon has 4 electrons. Here they are. Okay. A good relationship means if you want a bond, you give 1 and the other person gives 1. Remember, hydrogen has only 1 electron. Are we all in agreement with that? Hydrogen has 1 electron. So it definitely needs to be, it's going to look like that, right? So hydrogen with its 1 electron. So hydrogen wants to get to 2. This is perfect. Hydrogen wants to get to 2 because the first row, remember the first row, you only need to get to 2 to be full, right? So hydrogen's like, hey, I need 1. Carbon's like, I really need 4, but you're giving me 1. I'll take 1 and I'll make a relationship with somebody else. So these two give 1 to each other, right? And just like that, that carbon is now sharing 2 electrons with that hydrogen. That is equivalent to 1 bond. 2 electrons is equal to a bond. When you share 2 electrons, you are now in a bond because those electrons no longer belong to you independently. They belong to both of you. And so they're going to reside in between the 2 of you. You get to share them, but you can count them as yours, right? That's the pot, right? The pot of money, the pot of electrons that now is the foundation of that relationship. Carbon is still not satisfied, right? So carbon is like, I'm up to 5. So I need more. So what carbon does is that it shares with another hydrogen that needs 1. It shares with another hydrogen that needs 1, right? And it shares with another hydrogen that needs 1. And all of a sudden, carbon is making 4 bonds, right? Each bond is 2 electrons. So what we do now is instead of writing it like that, where we have the 2 electrons in between, we just represent them as bonds. You could have put the 2 electrons like that. You didn't have to write a line. It's either or, right? But because we know that those electrons are being shared between 2 atoms, we call that a bond, right? So this is a bond, okay? And this is a very good bond. I'm just letting you know. Carbon and hydrogen make a very nice, strong bond. Those 2 will stick together, right? Very well, right? It's not like oxygen and hydrogen. That bond is kind of sus, right? But this is a very good bond. Now, what you just learned is how to derive how many bonds an atom makes in a covalently bonded scenario. We just looked at ionic bonds where they just give up their electrons. But in this case, we're looking at when the sharing happens. So think about it. Let's simplify it for you so you can always remember this. If you need to make a bond, if you need an electron, you got to share an electron to get an electron. That's the real rule that you should follow. So if carbon has 4 electrons, which we know from the periodic table based on its position, it needs 4 more to get to 8. Which means it needs to share 1 to get 1, which means it needs to share 4 times. You need to share 4 for 4, right? This isn't a Wendy's, but 4 for 4, right? You need to share 1 to get 1. And so, therefore, carbon makes 4 bonds, okay? So you can do the same thing with every other atom, right? So, for example, nitrogen. How many electrons does nitrogen has? Nitrogen has 5 electrons, right? Nitrogen needs to get to 8. Does that make sense? So if nitrogen needs to get to 8, it needs to share one to get one. So it needs to make 3 bonds. Does that make sense? So because of that, nitrogen would make 3 bonds with hydrogen. And it would still have 2 electrons that belong to it that it never shared because it doesn't need to share as many. And that will get it to 8. And hydrogen always just wants to make 1 bond, so it's going to get to 1. So it just needs to get to 2. And so the way I think about it, again, is yes, it can only share with 3 hydrogens. I see that, right? It can only share for now, in its neutral state, when it's neutral. And so what this means is nitrogen is going to look like this, right? To reiterate or bonding, there it is. Perfect. We're good. That's how you draw the Lewis structure. You just drew your first Lewis structure. But the way I think about it is you're going to make as many bonds as you need to get to 8. So we can then predict how many bonds atoms are going to make. Carbon has 4 electrons, so it needs to make 4 bonds to get to 8 because it needs 4 electrons. Nitrogen has 5 electrons. It needs 3 more, so it has to make 3 bonds to get to 8. Oxygen has 6 electrons, so it needs to make 2 bonds to get to 8 because it needs 2 more electrons. And fluorine has 7 electrons. It needs to make 1 bond because it only needs 1 electron to get to 8. And these are the patterns that are going to persist throughout drawing molecules. All right, there's an exception. We'll talk about it shortly. You know, life isn't anything without exceptions. And with this in mind, we can literally draw almost any molecule. So now let's start drawing the molecules that you were seeing on the first pages, right? We're actually at 8:05. Look at us. We're going like, oh my God. Let's get through this page and then we will wrap up and pick it up again on Saturday. I am recording these and I'll post them. So we'll wrap up and then we'll go into Lewis structures. But let's do a quick Lewis structure, right? To talk about it. So we already did Lewis structures, right? But look, to put it into words, Lewis structures really show the 2-dimensional connection of atoms. We saw the 2D connections, the lines and the right are the connections. But molecules actually are 3-dimensional, and we're going to get to that later. But for now, we're focusing on the 2D as we draw it in 2 dimensions on our page. And so that's all a Lewis structure shows you. And what you've already learned about Lewis structures is that you just need to know about the valence electrons. It really shows you the valence electrons, ones in that outer level that's not filled. We know the inner level ones are there. We don't need them. They're filled, they're unreactive. So really it shows you the ones that are at the outer level, how they're being shared with other atoms to make bonds. And then as I showed you, 2 shared electrons, we represent them as a bond, and that is a line. Whenever the electrons are in between, we just draw a straight line. We're like, hey, it's a handshake. There are 2 electrons here, and they're shared between these 2 atoms. And then finally, the ones that you don't share, we call those lone pairs. We draw those as dots. And oftentimes we don't draw them, but for now you're new at this. But we draw them on the atoms to show that they're there. Sometimes we don't draw them because we know they're there and they're just implied. Okay, so let's do a quick one. Let's see if you can draw a simple Lewis structure. We just did ammonia. We have water. We have, let's do, for example, CCl4. First of all, CCl4, is that a molecule or a compound? That is definitely a compound. Very nice. Okay, so let's see how we can draw this, right? We have 2 different atoms in this molecule, in this compound. See, I should film my own class. We have 2 different atoms in this compound. We have a carbon atom and we have a chlorine atom. Does everybody recognize that? Those are the 2 different atoms. We have 1 carbon atom and we have 4 chlorine atoms. And the question is, how can you put that together in a Lewis structure where you're showing the bonding and you're showing the electrons and where they are? We have to think about whether this is going to be a covalent bond or whether this is going to be an ionic bond. So that's the first question. Is this ionic or covalent, right? So we need to know what to draw. Are we going to draw a plus minus, or are we going to draw bonds? Now, how I know this is covalent is because carbon is involved, right? Carbon is not making a plus charge. Carbon is not really making a minus charge, at least for our purposes for now. So it's more than likely a covalent bond, right? And so because it's covalently bonded, we know already how many bonds carbon makes. Carbon is number four valence electrons, right? So carbon has 4 valence electrons. So carbon must be making 4 bonds, right? We know that chlorine is group 7. It wants 1 more electron. So it must be making 1 bond as well. And so this would be the Lewis structure for this molecule. And you can check the electrons, right? You can check the electrons. Let's check the electrons. Carbon brought 4 to the table, but now it has access to 8. Does that make sense? So it is very, very happy. So we know it's not positive or negative because I didn't write a positive or negative charge. If we had a positive charge here, that would tell you. We'd have to write that. I could not write it. I would have to tell you because you wouldn't know otherwise. Does that make sense? You could know eventually, but for now, I will write it. So you can see those 8 electrons. Carbon is very happy because it's bonded to 4 things. And then you can think about chlorine. Chlorine is also happy because it has 8 electrons. It had 6 that it owns, and it didn't share. It shared 1 of its 7, right? And carbon shared 1 with it, so it has access to 8. And so this is a very happy molecule. All of these atoms are very much pleased with all of the electrons, and we can track where they are with these 4 bonds. Does that make sense? So this is a good structure. So the octet rule really comes from all of this. Literally, this is what we're saying. The first row elements, hydrogen, only wants 1 bond because it needs just 2 electrons. The second row elements on the periodic table, those need to get to 8. The third row also needs to get to 8 and sometimes 18. We're never going to do 18 for now in this class. We're not going to do transition metal stuff. And we're going to end with this. So there are some exceptions to the rule. Boron. And if you look at the periodic table, boron only has 3 electrons. Does that make sense? Boron only has 3 electrons. This is a problem for boron because boron wants to get to 8. If it's going to make a covalent bond, it has to share 1. But you can only make as many bonds as you're willing, at least in the neutral state, as you can share, right? For the most part. You can make more, but if we're looking at covalent bonds, based on the atom sharing with another atom, it can only share 3 because it only has 3. So boron has 3, right? It could share 1 of its electrons with, say, a hydrogen, but it can only share with 3 hydrogens, right? Because it doesn't have any more electrons. If it wants to make another bond, those electrons have to come from somewhere else, right? And so what you're going to get is boron making 3 bonds. In this situation, boron never gets to 8 because it doesn't have any more electrons, right? And this is fine. It's not stable. This is not very stable. It's very reactive. But based on what it can do with what it has, this is what it can do. And this is okay for boron because that's all it can do in this situation, right? Does that make sense? So you really have to share 1 to get 1. That's why I like to explain it that way. But then you have other atoms that can actually accept more in the opposite direction. You have atoms like boron that can make less bonds that get it to 8. But then you have atoms like sulfur and phosphorus that can make more bonds that get them beyond 8. And a good example of that is an atom we were talking about. I'll just show you the structure. This is sulfuric acid. Here is sulfuric acid. This sulfur has access to how many electrons? I want y'all to count. How many electrons does that sulfur have access to? You can tell by the bonds. Each bond is 2 electrons, right? Remember, our lines are 2 electrons. So that sulfur has access to 12. There are 6 bonds that it's making, right? 6 bonds. It's making 2 bonds to the oxygen at the top, 2 bonds to the oxygen below it, 1 bond to the oxygen on the left, 1 box to the oxygen on the right. This means this sulfur has 12 electrons. This is a greedy sulfur, right? But some atoms can have expanded octets where they have lots of electrons around them. So we've been really, really focusing on single bonds a lot. You see in a double bond right now where an atom can make 2 connections to the same atom. Your job will not be, at least in this course, to know when an atom makes more than 8. Everything I ask you to draw, you are going to assume that that atom is making 8. This is just an example to show you that it's making more than 8, and you will get comfortable with ones that make more than 8 eventually. But if I ask you to draw something, I'm going to ask you to draw something that has 8 to simplify what we're learning. So you never have to guess. But here's an example where if I draw the structure, you'll be able to like, oh, that one is making more than 8. Its octet is expanded. It's beyond 8. But your job is to make sure everything makes 8. So now if you look at the oxygens in this molecule, let's end with this. If you look at the oxygens in this molecule, it is actually happy. These oxygens have 2 lone pairs on them. And if you look at that, that means it's 8. If you look at this oxygen, this also has to be 8, right? If there's no charge on the atom, it must have 8 electrons. And so you must add the number of electrons that give it 8. If it doesn't have 8, I would put a charge on it, which would tell you how many electrons you have, right? And so that's what we have to think about. This oxygen up top also has 4 more electrons to make it 8. And then this one also has 4 more electrons to make it 8. I hope you see a pattern here. Every single oxygen, when it is neutral, will always make 2 bonds, and it will always have 2 lone pairs, right? And those 2 bonds can be singly bonded to 2 different things, or it could be doubly bonded to the same thing, right? It doesn't matter. As long as it's making 2 bonds and it's making 2 lone pairs, that is. Each line is 2 electrons because each bond is a shared relationship. Remember, every time we have a line is a bond, which indicates you're sharing one. And the atom you're in a relationship with is also sharing one. So each bond is 2 electrons. And so that is how we do that. Okay? All right. I think I'm going to end here. I will take maybe 2 or 3 quick questions. I will stop the recording and I will post this on YouTube, I believe. I have a channel already. I barely ever use it, but I will post this on YouTube for those who want to revisit, and I will maybe put some questions on the website so you can do some practice if you want. And Saturday, we're going to get into the real organic stuff where you're going to learn how to draw all of these molecules. So Star, I see your question. How do you get to 12? You didn't get to 12. This molecule got to 12. And that's what I'm showing you is an exception when that sulfur got to 12. You won't necessarily know when that's happening unless you see it. If I ask you to draw something like a carbon atom, you're going to assume that it wants 8. And you're going to make connections so it gets to 8. If I draw a different sulfur molecule, for example, this sulfur has 8. And that's normal for sulfur, quote unquote normal, but it can have more than 8 is what I'm trying to say. You won't necessarily know when that's the case. And my point is I'm not trying to ask you to always figure that out. Does that make sense? Hopefully that clarifies your question. Any other questions on the chat, people, and on TikTok Live? People have any questions before we head out? Next class is Saturday at 7 p.m. same time. The link is in my bio on my TikTok page. It'll be the same Zoom link, same format, and we'll keep going. So thank you all for coming. I will see y'all on Saturday and enjoy the rest of your night.